Okay, before I start, is there any questions maybe about the assignment or about the content from last lecture? All right, see none. Start on your assignment. It's not hard work necessarily, but it is a little long. So there's a lot of different things that you have to do. And it requires some creativity too. So if you leave it for the last minute, then it will be hard to like brainstorm. You'll be like stressed about like coming up with the criteria and things like that. And they just won't come to you. So it's something that if you start early, you start thinking about it. And then when you think about other things, you might have ideas about the assignment. So yeah, I would encourage you. Of course, everyone wants to start early. And everyone intends to, myself included, but we never do. Yeah. Right.
Like in this scenario, we'll check the physical card system, cubic system, and online system, and compare it with like security evaluation properties.
Yeah, yeah, that's right. Yeah. So the let me just pull up the chart from class. So your three systems will be like rows in the table. And then the columns that you're coming up with, what you're doing basically in the assignment is you're coming up with the U columns, the D columns, and the S columns. Yeah, come in. And then I'll have you evaluate, like do the dots just for one system, not for all three systems later in the question. Yeah. And so the security, usability, and deployability criteria that you come up with, they should separate the three systems, okay? So you'll look here, like if you look at this diagram, there could be some security property where everyone gets a full dot. That's not really a good security property because they all get it or they all don't get it. So you'll notice that for each one of these columns, some of them are getting it, some of them aren't, right? So it's telling a sort of complicated scenario, right? So that's what I'm looking for in the security, deployability, usability. If there's one column that you really like and you want to showcase that no one gets that dot, then that's fine, or that everyone gets that dot. If you think it's really important, it's an important property, then that's fine. But I don't want to see like on most of your columns, they're either all getting it or they're all not getting it. So the criteria that you should come up with should show the differences between the three systems.
In security criteria, like while we explained in the class, there is a scenario like resilient to like
Yeah.
or something like that.
Sure.
Can we use those
Yeah, so if you think that one of the ones from the passwords applies to your case, then you can use it. I'm hoping that you come up with some new ones that aren't specific to passwords, but yeah.
And in security criteria, like resilient in the sense of withstand something?
Yeah, resilient just means that it resists something. And you don't have to use that word resilient. You can say it resists or it stops or something.
We should come up with a positive.
Yeah, so that's exactly why we were using the word resilient, is because we said, oh, there's this attack, and then the opposite of that is that you stop that attack from happening. And that's something you want. You want to stop the attack, right? And so when you want to flip it to a positive, then that's why that's why that, like, everything's resilient to this, resilient to that kind of thing. Yeah. Yes?
Yeah. For question one, you said here, then state if the other systems, physical card and online, are different in terms of scoping. Can I, in terms of bad things and good things, or I should specify only the good things?
No, good and bad things.
Both.
Yeah. So if there's attacks if there's vulnerabilities to one system, then you can point that out. And if some of the systems have better defenses against spoofing attacks, point that out as well. Yeah. Other questions? Okay, just a reminder, I do have office hours tomorrow at 1, so if there's any, if you have any questions between now and then, you can ask them. Otherwise, they're going to be due in class, so it's, try to at least look at the assignment, read through it before tomorrow at 1. And then I guess if you have a slip day, then you can ask me next class about stuff. But yeah. Okay. All right. So that's it for the assignment. No questions about last lecture. All right. So I looked into extended validated certificates. So remember that these are the ones that would say, oh, you've connected to, Twitter Inc. as opposed to just twitter.com. And so it seems that about a year ago, all the browsers got rid of signaling to the user whether you're looking at an EV or DV certificate. So yeah, usually I would take this course to point out that it was kind of flawed to begin with because you couldn't tell the difference and most people didn't know the difference. And like if something's green or not green, you don't know. And so the browsers eventually came around to thinking the same way. And so they said, let's just get rid of it. So that's the case there. Okay, so what I'll talk about next are DV certificates. So DV, remember, is that you're just validating that it's twitter.com. You have no idea whether that's actually Twitter, the company, or not. And this is how the validation process is. How does the CA figure out that it's talking to twitter.com? Or basically what will happen is someone will come to the CA and say, here's my key, right? Here's my public key. And remember, if you have the right public key, the tunnel ends at the public key, okay? So if we want to zoom all the way out, we're trying to break HTTPS. We're trying to break it by getting the tunnel pointed at us. And to get the tunnel pointed at us, we need a certificate authority to say that our public key is Twitter's public key, even though it's not, it's our public key. Okay, so you can go to a CA, anyone can go to a CA and say, hey, I'm twitter.com. This is my public key. Okay, there's nothing stopping you from doing that. But then the CA is going to say, oh, really, like, prove it. Okay, and so the question is, how do they say, like, what do they do to prove it? Okay. So I'll say the requester is the domain they claim they are. All right. And the other thing is the reason that we have DV and EV is EV is an in-person process. So they check, people look at documents and things like that. They'll talk to you on the phone, whatever. DV was introduced because EV was too slow. So in the early days of certificates, there were just EV certificates. And that was too slow. It took a couple days to get certificates. And let's say you forgot to renew your certificate. We'll talk about this a little later, but certificates expire. Then it's like you realize that like you start getting emails from your users like, hey, I can't connect to your site. There's this scary warning. It says that the certificate's invalid. And then you're like, okay, I have to go renew my certificate. And then if you're in an EV world, that's like a 3-day process, right? At least. Might be a week process, maybe 2 weeks, whatever. And so, you can't have your website, if you're an e-commerce site, you're not going to have your site down for 3 days because you need a new certificate, right? So what we want is an automated way to determine this fact. So how does the CA figure out the requester is the domain they claim? And we want this to be fully automated, at least for the CA's perspective. So if the user has to do something, like if there has to be a person on the user side, then that's fine. Ideally, you would have it fully automated on both the person who's requesting the certificate and the CA, but you definitely want the CA to be fully automated. Okay, and so the basic protocol works as follows. It uses email. And so you'll show up at the CA and you'll say, I want a certificate for domain.ca. Sorry, I'm having some lag on this program. So what the CA will do, and this is a computer, not a person, but what they'll do is they're going to choose a secret, like a password or a key or a nonce, whatever you want to call it. Just call it a secret value. And they're going to email that value X. It's like a challenge. And basically what they want to do is if you actually are domain.ca, they're going to email it to domain.ca. Now, domain.ca is not an email address, right? It's just a domain. And so what they want to know is if you control the domain for domain.ca, then you must control all the email that goes to domain.ca as well. And so if you can show that you control the email that's going into this domain, then we'll believe that you actually own the domain. So what they'll do is it's just a convention, but by convention they'll send the value X to the email address admin@domain.ca. Okay, and then if you actually control this email address, you'll fetch that value X out of the email, and you'll submit it back to the CA and say, look, I must be from domain.ca because I can tell you what the value is that you sent me. And you'll send it back to them like through their website. And this is presumably over HTTPS. So you have HTTPS when you're dealing, the CA has HTTPS already, so that's fine. So you connect to the HTTPS, you say, okay, I'm gonna add, one certificate to my cart, and then they're like, okay, what's your domain? And then they send the email, and then they're like, okay, what's the value you got? And then you type it in, and then it says, great, I now believe you, so then I'll give you a certificate, and then you get your certificate automatically, okay? After you pay, usually. So you can download your signed certificate. Okay, now let's say you're an adversary and your goal is, as always, we're in a man-in-the-middle position. We want to break HTTPS. We're going to do it by getting the tunnel pointed at us. And to do that, we need to get a certificate for a domain that we don't control. All right, so now you know the process that the CA is going to use. Is there any vulnerabilities in this that you can think of? Or is there any attacks that you could do on this little step-by-step procedure?
I have access to the admin email.
Okay, so if you have access to admin@domain.ca, then you can get a certificate for that website, and then you can impersonate that website. How would you get, why would you get admin at domain?
I do phishing to the admin, and I got the password.
Okay. So the first idea here is, okay, we're going to attack this inbox. So I'll just write down attacks. All right, so in terms of a tree, it's sort of like, okay, if we can get access to admin@domain.ca, then we can break the whole system. And so recall that usually it's a password that protects an email address, okay? So if you can break that password, then you can get that email account. If you have access to the email account, then you can get a certificate, then you can impersonate the whole website, okay? How you get the password, do whatever you want. So you could use phishing, you could guess it, you could have a key logger on the computer, whatever, infect it with malware of the person, the actual administrator, whatever, however you want. So this could be a whole attack tree itself, but you get the password, then you're in. Is there another way to get access to that email address? Okay, so all email is directed to, like in order for email to leave the CA's computer and to end up in the inbox at admin.domain.ca, the email has to get routed to a server. Okay, so domain.ca throws up a server, a mail server that accepts incoming email, and then that server will give it to the right address. Okay, if you can get your mail server get email sent to that domain directed to your mail server instead, right? Then you're going to get all that email. So you'll get admin@domain.ca. Okay. So how do I know what the mail server is for domain.ca? So I'm an email client. The CA just sent the email, and I have to figure out, you know, where am I sending this email to? I'm sending it somewhere on the internet. Where's it going? Okay. So actually not reverse, but just normal DNS. So it's the DNS protocol. So just like if I was visiting domain.ca, I would use DNS, and there would be a record that would say this is the IP address of the website. And there's another record called the MX record for mail server or mail exchange, and it might have the same or a different IP address depending on how the website's set up. Okay. Now, how do you get things into DNS? So how did DNS learn that that the domain's mail server is 8.8.4.4 or whatever it is?
From the master name server, there is master is slave and DNS.
Okay, so DNS has its own hierarchy,
Yeah.
but don't even think of that. Like DNS, just take DNS as a whole. Forget about how DNS works internally. DNS somehow knows that this IP address belongs to this domain. How did it know that in the first place?
There is like text files and that you insert to type, and that's how it's done.
Okay, who's you in that sentence? So you said there's files that you type.
The admin type, like
The admin of
the domain.
Okay, so the admin of the domain put it into DNS.
Yeah.
How does DNS know that this is the admin of the domain? Like, why can't I just be like, I'm the admin of domain .ca, please change the IP address to blah, 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 blah.
Every domain has an authoritative name server, so it has a particular name server that says that, okay, say for example, it can be someone like GoDaddy. So GoDaddy can, if I register my domain name with GoDaddy, then GoDaddy is the authoritative name server, then only GoDaddy can change that domain name.
Okay. So it all goes back to the very start. So at the start of time, someone registered that domain. Okay? And when they registered that domain, we don't have to get into the technical details, but just think of it as they created an account, username, password with GoDaddy or whoever they registered it with. And if you can have access to that account, then you can change the mail server, the IP address of the server, whatever you want to change. Okay? So if you can get access to the DNS record for that domain, then you can change the MX record or basically where the mail points, and then you can hijack the mail. Okay? And what is it that stops you from getting access to the DNS record? It's another password. Okay? Usually. It could be two-factor authentication or whatever, but. So it's actually kind of crazy because HTTPS was this like cryptographic protocol, and it was meant, we're using keys, we're not using passwords anymore. We're using big, long cryptographic keys. They're super secure. No one will ever guess them. And yet the whole system comes down to if you can get some passwords to the right things, then you can break the entire thing, right? Okay, anything else you can think of? How else could we get these emails?
Figuring out the code.
Okay, go ahead.
Figuring out the code.
Okay, so we could try and guess X. So that's possible. So generally what would happen is X would be too long. The CA should choose one that's too long. So maybe they don't, then you could definitely exploit it. Yeah, so the countermeasure here would be it should be too long to exhaustive search. Or they shouldn't let you try multiple times, either way. But it is a fully automated system, no humans. Okay, any other ideas?
Sir, there is a probability if there is a IDO in domain.ca where our domain name is registered, we can create an alternate email like that by exploiting the GoDaddy.com.
Okay. What do you mean by alternate email?
There is a, suppose I register my own domain name,
Yeah.
but if I exploit insert direct object reference vulnerability in my domain, but I change their domain name, I will register my own email
Okay.
for their domain.
You shouldn't be able to use your own domain to do anything.
I just create my email, but I will use their domain name.
Yeah. So you say that your email is whatever at their domain.ca. Yeah. And remember, some websites will let you do that, right? Like Gmail, for example, I can create whatever I want at gmail.com. And then what do you do?
No, I mean there is a vulnerability in GoDaddy.com.
Yeah.
If I exploit it, I can create email in domain.ca.
Okay. All right. So there might be some exploit with GoDaddy and things like that. But let's go back to the idea of you choosing your own email address. So there are websites that let you choose an email address, right? So could you just go to Gmail? Like probably someone's already done it, but could you go and ask for admin@gmail.com?
Of course not.
Why not?
They will restrict it in the code.
Okay, so Google engineers are too smart, right? But what if it's not Gmail? What if it's Concordia Mail?
We should try.
Yeah. Okay, so maybe they're smart, maybe they're not. What if it's not admin? Does every CA use admin? What if the CA is in somewhere else in the world, they don't even speak English? Admin is short for administration. That's an English word, right? Could there be a CA that uses another language and they have admin in that language as the email? Possible, right? Do the Google engineers know about all of those CAs? If you could get a certificate from some CA in another country with emails in another language, could that CA issue a certificate for any site on the internet? Yes. Okay, so if you remember one thing from all these lectures, any CA can issue a certificate for any site. Okay? Weakest link. You find one CA that has one vulnerability, one of those, 50 root certificates and 600 intermediary certificates. You find any one of them that have a vulnerability, they can all issue you a Google certificate, a Twitter certificate, a Facebook certificate, whatever you want. Okay. So webmail is a problem. So I'll use the example of Live. It's like Gmail, Microsoft's version of it. Now the problem is that this is probably blocked, right? So Microsoft engineers too smart to let you go and register this domain. Okay, but other CAs may not use admin. In fact, most CAs actually have a whole bunch of like authorized email addresses, and you can choose the one you want. So like admin, host master, host, I forget what they all are, but there's a bunch of them. Okay, so there's others that are used. And there was one CA in the world that would actually offer SSL certificates at domain.ca. And so this was like only one CA. So like 1 out of the 600 CAs had this option. And Microsoft engineers, as smart as they were, they didn't know about this option, right? They can't keep tabs of what every 600, what all 600 CAs are doing. And so they didn't block this email address. And so someone actually went and they registered SSL certificates at live.com, and then they got a certificate. Now that person was a security person, and so they did it just to prove a point, and then wrote about it. But yeah. Sorry, this is being really laggy. I can't seem to erase that line, but whatever. I'll erase it later. Let me, I'm going to actually try the old version of this software, see if it works better. I just updated it and it. Hopefully this goes better. Okay, so I'll actually put in live.com because it's a real example. Okay, a couple other ideas is we could just intercept the email. So our email's encrypted. If you're in a man-in-the-middle position and the email goes across, you're seeing all the traffic going across, so there's a chance that you're going to see the email go across too. Could you just lift the email out? And so the answer is kind of complicated. It turns out that email it's encrypted between servers along the line, but it's not encrypted end-to-end. So the short answer is yes, if you're an active adversary, you're in the middle, you can intercept email. So email is not encrypted, essentially. So it's kind of like there's a tunnel to one mail server and then another tunnel to another and then another tunnel to another. And so if you can get on one end of those, all the little tunnels in the middle, or you can put yourself when it exits one tunnel before it goes into the other, then you can read it. Okay, so anyways, that's a bunch of attacks. So you can see that this whole process that's used, this email validation process, it looks good at first, but then when you start digging a bit and you're like, okay, email's protecting it, well, what protects email? And what protects the mail server? And what is there encryption on email? Can you guess passwords? Those kinds of things. You see that, oh, it actually starts to break apart. All right. There's two other ways that you can do fully automated. One is that you just put, so if I want to register domain.ca, I show up and I say I'm going to register at domain.ca, and they say, okay, if this is really you, put your certificate request that includes your public key, put it somewhere on your website, like put it in /ssl.txt or something like that. Then the server will go, the CA will go, they'll look, and if they see that file there, then they'll believe that you control the domain. So the ability to insert files at arbitrary locations within the domain proves that you own the domain. And basically the same kinds of attacks apply. If you can hijack the DNS, then you can have them point at your website where you have the file sitting there as opposed to going to the real website. If you can guess the password to do that. If you see the traffic going across, we're going to assume it's not going over HTTPS because they're buying a certificate in the first place. So you might be able to, even though they go to the website, like the real Google, they look for that file and it's not there. So Google sends back a 404 file not found error, and then you replace that file not found with the request that you want. So the CA, it looks like they were able to successfully retrieve it. Now, in this case, you would have to be a man in the middle between the CA and the website. But anyways, so that's another kind of attack. And another thing is, since this all relies on DNS, why don't you just put it in DNS itself? Like, why don't you just put your public key in DNS? Because I'm going to use DNS to look up your email or to look up your domain anyways. And so I should also note that there's a better way of doing this with APIs now that's just faster and more automated, but it essentially ends up being the same thing. So you can put certificate requests in DNS. And this actually you could run this logic further than it actually is run. So in this case, we put our certificate information in DNS so the CA can verify it. And if the CA can verify it, then they'll issue us a certificate, they'll sign it. Then when users come to our website, then we'll give them the certificate that the CA signed, and they'll believe that they're talking to us because we have a signed certificate, right? But why doesn't the user who's trying to connect to our website just look up our key in DNS? Then we don't even need CAs at all, right? Like the user could just go directly to DNS. And so there is a proposal called Dane to do that. And for a variety of reasons, it isn't a reality yet. But if I teach this course for another 5 years, maybe we'll all be using Dane instead. So I'll just show it to you because it's kind of fun. So here's a user. Here's the admin. Here's like DNS. And here's like the CA kind of thing. So basically the admin puts the certificate request, which I'll call I forget, there's an acronym for it. But anyways, I'll just put actually, let's keep it really simple. I'll just say, okay, you put the public key in the DNS, then the CA comes and they're like, okay, what's the public key for this domain, right? And they get the public key. Then they're like, okay, here's your certificate. Then when the user connects to you, they're like, what's your certificate? And the domain is like, oh, here's my certificate. Okay, so that would be like the current process. Okay, and instead, what we could do in Dane is here's the user, here's the admin, and this technically could be like the server as well as the actual human being of the website. Here's DNS, here's the CA. So the admin will put the PK in DNS, and the user's like, okay, they don't actually need a certificate. They want the certificate because it has the public key. They just need the public key, right? So they're just like, okay, what's the public key for this domain? And then DNS says, oh, this is the public key. Okay, so that's much simpler. You don't need the CA. Way simpler process. And so anyways, why this hasn't taken off is too complicated to explain now. But like I say, eventually in 5-10 years, this might be what we're using, and we might not talk about CAs ever again.
You can verify, like as a user, you can verify the identity of the domain.
Yeah, so what I didn't put in the request, but when you ask for the PK, you're like, here's the domain, right? And I want the public key for that domain. Is that what you mean, or?
Since it's not signed.
Okay. So then there's the question of, well, what if somebody's in the middle between you and the DNS server? Then they could swap out the key for something else, right? Yeah. And so that applies equally in both cases. So that's one of the arguments against stain is in both cases, if you're an adversary and you're sitting, just give me a sec. So if you're an adversary sitting here, then you can swap out the public key when it goes back to the CA, and then you can hijack the whole system. And similarly, if you're an adversary standing here, then you could swap out the whole system. And so the main argument actually for this system is it's harder for an adversary to get between a CA and DNS than it is for an adversary to get between an end user and DNS. To get between an end user and DNS, I just take over their computer, I take over their Wi-Fi router, I am the ISP, there's lots of things. A CA can actually run its own DNS resolver. So this whole thing can be internal to the CA itself. So
over here we can also change the public key so
yeah, that's what I meant. Yeah. So you would actually modify it to be the adversaries. Okay. Now, all of this is possible because DNS itself isn't encrypted. And you don't even need encryption, you don't need secrecy, you just need integrity. And so there's no integrity on that connection. So if we could get DNS records to sign things so that when you got a response back from DNS, you knew, oh, this is what the DNS server said. Even if there was an adversary in the middle, they didn't change it because they couldn't have forged that signature. Then this stain system works. And that's actually what's holding it up. So what's holding it up is we have a protocol for doing signed DNS called DNSSEC, but it's slow and there's been low uptick and there's a bunch of kind of performance reasons and things like that. So once we get DNSSEC rolled out better, then we can go to Dane. But yeah, so that's actually the long, complete story of why we don't have Dane yet. Okay, other questions, comments? Yeah.
Why DNS is not encrypted?
So it's not encrypted because in order for it to be encrypted, then you have this original problem of how do I know the public key of DNS, right? And so anytime you have an encrypted, you have a tunnel, and then you want to know the tunnel ends, and now you have to ask, well, does it end at DNS, right? And so we're trying to solve this problem of where the tunnel ends, and we just keep pushing it around. We're like, does it end with the user? Well, yeah, because the CA says it ends with the user. But how do you know that the CA signed it? Well, the CA knows it signed it because of DNS. Well, how do you know that DNS signed it or whatever? So it was only recently that they developed a key infrastructure for DNS. So now DNS servers have keys, so they are able to sign things. Your computer comes with those keys. They're hard baked into the computer. There's only 2 CAs, root CAs for the whole DNS system. And so, yeah, it took a while for basically the internet people to settle what that infrastructure should look like. Now it's in the computers, and it's on and you can use it, but for performance reasons, a lot of people don't use it. Okay, other questions? So in general, this is actually, the deeper answer is that in the early days of the internet, nothing was encrypted. So everything by default, there was no encryption. There wasn't even security, even access control. If you put a website up, anyone in the world could go and change it if they knew what they were doing. And then eventually we said, okay, well, we need to put passwords or, you can only change it if you're on this computer and put some access control on stuff. And then we introduced encryption. Then we got it so that encryption wasn't considered a weapon and you could actually use it. And so basically DNS is as old as the internet itself. And so it just wasn't encrypted because nothing was encrypted in the early days. Yeah. So whatever encryption security we have, they're all add-ons that have been added on to these protocols after the fact. Other questions, comments? Okay. So the lesson that we might learn from all of this is that so CAs are not actually authoritative over which public key belongs to which domain. What do I mean by authoritative? I mean, like, they have some insider information. Like, CAs don't know what Twitter's public key is any better than you would, right? And so they have to figure it out from scratch. They don't have special information or anything like that. It's not like the Twitter had to go to the CA or to choose a public key or something like that. They're no more knowledgeable than anyone else, okay? And basically, at the end of the day, what they do is they say, I can't figure out what Twitter's public key is, so I'm going to rely on email or DNS or something else to basically figure it out for me. So they just redirect to DNS. Okay, so when you see those lists of 50 companies in the certificate lists, yeah, they don't have any special information, right? They're using DNS or the same way that you could if you want to figure out whether someone actually controls a domain. They're not really doing anything special. Okay. Now, the next thing is, remember, we're trying to get this tunnel pointed at us. So here's the user. They're connected to the server. Okay. And in order for all of this to happen before the tunnel, basically, the user would first connect to the server. I won't show that, but they'd be like, okay, I want to do a secure tunnel with you. And the certificate would, or the server would say, okay, don't worry, I have this certificate. Why don't you take a look at it? And if you believe it, then you have my public key. It's in the certificate. Then we can do some crypto magic and we can get this tunnel up. Okay. And so the user has to check whether the certificate is valid. Okay, so it's going to check, is the certificate actually signed by CA, and do I know who that CA is? Okay, so by saying, do I know who that certificate CA is, it's like, do I know the root certificate of that CA? Do I recognize them because they're in my list? But they might not. They might be an intermediary. So then I'm going to see, well, is there this certificate chain where that intermediary certificate was signed by another CA and that CA was signed by another one and that one was signed by the root certificate? Okay, so that's the basic check. Now there's other checks as well. The first thing is, or another thing is, I'm trying to connect to some domain, right? What if I'm trying to connect to twitter.com and you give me a certificate for facebook.com? That is a valid certificate. It's signed by a CA. It's just for a domain that's completely different than the one I'm trying to visit, okay? So at a basic level, I need to check that the domain matches. So the cert domain matches the site that I'm trying to connect to. Another thing that you might not think of is, okay, you're able to, for example, let's say you actually own domain.ca. You're able to get a certificate for domain.ca, right? Let me just pull up a diagram that we had from the previous class to explain this. Okay, so I'm a website, so that's fine. I got this certificate. It's signed by some certificate authority. That certificate authority had its own certificate that was signed by some other certificate authority. It had one, and it was signed by a root certificate. Okay? What if I take my website certificate and I say, hey, I'm a CA. I'm going to go sign a certificate for someone else? Okay? What stops me from doing that? So like this certificate, this person, CA double double, they could issue a site certificate for any website on the internet. So why, now that I have a certificate, why can't I just issue a certificate for any website? Okay, so the answer is that this we know is a CA certificate, meaning they're allowed to issue certificates for websites because they're in the root list. Okay, when this CA got this certificate, it was different than our certificate because there's a field somewhere in the certificate that says this certificate is making this person a CA. Okay, it's not just that we're signing that this is their public key. We're signing that this is their public key and they're allowed to be a CA. Okay, so that flag will be turned on. When you get a site certificate, then that flag will be turned off. So it will say, yes, I am certifying that this is your public key, but this site is not allowed to be a CA. Okay, so they're not allowed to go and issue certificates. Okay, but you need to check that. When you get a certificate and you see this chain, you have to check that the CAs in that chain are actually CAs. They're allowed to be CAs. They're not using certificates that don't have that flag checked. Okay.
So what happens if a domain name is expired?
Good, good. So, well, let me add that. Okay, so I'll just pencil this in and come back. There was another comment.
The same thing. On the chain, if one of them is expired, after that they expire or?
Yeah, so then the whole chain is expired. Yeah, yeah. So let me show you this CA thing just so that you can see it. So here's Google. Here's their certificate chain. So you can see that there's a site certificate for google.com. It was issued by a CA called GTS-CA, and then GTS has a root certificate. So there's one intermediary. So root certificate, one intermediary, and then there's google.com. And while we're just thinking about CAs as a public key and a domain name, there's actually like a ton of stuff that are in certificates. So you can look through all of this stuff. If you're taking a crypto course, you'll recognize like a lot of these, the cryptography that's being used. But anyways, somewhere buried in this, there's a field called basic constraints. And you can see there's a certificate authority flag, and this is set to no. So that means that this is a website certificate. It can't go issue certificates for any other websites. But if we look at the intermediary, then we see under basic constraints that it's set to yes. And there's also a path length constraint, which says if it's set to 0, it means that you can create website certificates, but you can't create another CA who can then go and create web certificates. So you can restrict the number of CAs that you're allowed to create. So don't worry about that detail, but it's just for interest. And then the root certificate also is marked as being authorized, and there's no path length restriction on it. it's authorized to issue certificates. So it sounds really stupid, but there were early versions, like when Internet Explorer first came out, they didn't check that field. So you could take a site certificate and you could just pretend you're a CA, issue a whole bunch of websites, and they just weren't checking, the code wasn't checking whether that flag was set or not. And then you could issue certificates for any site. And you say, oh, that's really stupid, like, but this was like the early days of Microsoft, you know, whatever. We all learned our lesson. Then when the iPhone came out, the very first version, it made the same mistake. And so anyways, these things come around. And that was like decades after, you know, everyone laughed about it because it was so stupid, but then they made the exact same mistake. Okay, so certificate is not expired. And I should say that this is not a complete list of checks. It's just some of the major ones. But there's more specific things that you can check. And then what happens if you do get a website? Let's say you're actually Twitter, or like the real Twitter. You get your certificate, and then someone breaks into your server and they steal your certificate, and you realize it. Okay, so now there is someone out there and they have a certificate and they can impersonate you. What can you do? Is there anything you can do? And so the answer is there should be something you should be able to do something. And so the whole this infrastructure for HTTPS needs to have a way to do what's called revocation, or to revoke a certificate. So you need to say, oh, that certificate is no longer valid. Okay, and so we'll consider that's going to be a topic in and of itself, because it's a little complicated how it works and it's a little broken. But we're going to check as well that the certificate is not revoked. Okay, so these are a few checks. Now, what I can tell you is in the history of HTTPS, every single one of these checks, there's been some vulnerability with it. So at some point in history, someone somewhere didn't check that the domain matched, or didn't check that it was signed and it traced back to a root certificate, or it didn't check that the domain matched the actual website that you're connecting to, or it didn't check the basic constraints flag, or it wasn't handling expirations correctly, or it wasn't handling revocation correctly. Okay, so I'll give you a few highlights. So the first one I'll talk about is this one, the second one. So I'll just say there have been issues with all of them. All right, so here's a story. Story about 2, which is domain mismatch. This was a vulnerability. It was in S-Tunnel. S-Tunnel is Apple's OS. I want to say, well, they call it Mac OS now. I'll just put that. But it was like back before they called Mac OS Mac OS. It was quite a while ago. This is just vulnerability in the code. Okay, so this was just a coding error. But at the end of the day, it led to being able to exploit domain mismatches for reasons that I'll explain later. I like to show the example just because it's kind of cool how it worked. So I'm just going to copy and paste this in because it takes too long to draw out. Okay, so I'm not going to go through, obviously I'm not going to show you actual source code. It would take too long to explain, but I'm going to give you the essence of a piece of code that was in S-tunnel implementation. And it was in the specific part of the code that was checking whether certificates were valid or not. Okay, so basically there's some code somewhere that's going to go through these 5 steps plus other ones as well. Okay, so the code's going to go through and check all of these things. Okay, so this is what the code looked like for Apple's S-tunnel in pseudocode. Basically, they had a variable called error. And if there was no error found yet, then it was set to 0. And if they found an error, then they would change the variable to 1. Okay? And so the code would check some condition, and I don't know what condition's what, but let's just call it some condition. Like, does the domain match the website that's being checked? Okay? And if this condition held, they would write it into the error. And so I guess they would return an error. So they would return a 0 if there was an actual error. Okay, sorry. So the condition would check. It would be like a negative condition. So this should not happen. So for example, condition 1 might be, this certificate is not expired. If that's true, then let me think. This is throwing me off because the 0 and 1 is inverted from the way I'm thinking about it. Okay. Forget everything I said. Okay, so condition 1 could be, is the certificate expired? Okay, if it's not expired, then the answer is no, it's false. That's a 0. That's a good thing. We want a 0. And if it is expired, that's a bad thing. It's a 1. So we would set that to 1. And then we would check whether the error is not equal to 0. So we would say, this certificate was expired, so that's true. So we set error to 1. And now that error is 1, we're going to fail at any point. Okay, like we're going to fail regardless. It doesn't matter. We don't even have to check the next set of things because we know that the certificate's expired, so we're just going to fail anyways. Okay, doesn't matter if it's revoked anymore, if the domain matches or anything like that. And so what we're going to do is we're just going to jump down to this fail condition, and the fail condition is going to return an error. Okay? But if there is no error in condition 1, then we'll go on to the next condition, and we'll check it. And then if there's no error there, then we'll go to the third. And eventually, if there's no errors all the way along, we'll get down to the fail condition, and we'll return error, but error is going to have a 0 saying that there's no error instead of a 1. Okay? So this code was great. It was actually, if I recall correctly, it was actually open source. So Apple doesn't open source everything, but this library they had open sourced. And I don't know how many people checked it. But anyways, there was one problem with the code, and it was really, really simple. Somewhere along this chain of checking, someone had accidentally probably copied and pasted the go-to fail twice. All right, so this became known as the go-to fail error. But anyway, so that's it. So the code was exactly correct, but there was 2 copies of go-to fail at one of the conditions. All right. So what happens in this code in this case? So let's start at the top. So let's assume that condition 1 is actually false. So there's no error. So that's fine. So this if statement does not hold, right? So this if statement, the if isn't true. Therefore, we're not going to execute go to fail, right? So if this, but it's not that, so we're going to skip over that line, okay? Then we go to condition 2. Let's say that condition 2 is not true as well, so there's no error with it. So error is equal to 0. Then this if statement is not true, right? So then we're going to skip, right? What are we going to skip? All right, so we're going to skip the next line, go to fail. And then are we going to skip down to here?
No,
Why not?
because there are no places.
Okay, so if this was in brackets, then we would skip both of these lines, go to fail, and then we would just go on to the next one. So if this was in brackets, basically it doesn't matter that there's this extra go to fail line. But they're not in brackets, so if they're not in brackets, what does that mean? Means the next line is the line that's the subject to the if statement. And then when you're done deciding about whether you execute that line, then you just go on to the next line of code, which is go to fail. Okay? So what that means is that if the code reaches basically this condition and it's not true, it will execute go to fail. Okay? So if the code makes it this far, it's always going to hit go to fail and it's always going to execute it. Okay? So what happens when it executes go to fail is it does what you think and it goes to fail and then it returns error. All right? So if you made it this far, so let's say you started here and you made it this far, whoops. Okay? And there were no errors. So error is still equal to 0 by the time you reach the end of this line. Then you're going to go to fail. You're going to turn to 0, which says that there was no error in the certificate process, right? All right. What about all of these, all this great code right here? Okay, so this code will never get executed. So it's basically it's unreachable code. What about all these things that you're checking, like condition 3 and condition 4? You're checking, like, is the certificate revoked? Do the domains match? Does the public key actually match? Is it actually signed by CA? What about all those conditions? So we're just going to skip them? So yes, that's essentially what this code did. So because somebody copied and pasted go to fail twice, now conspiracy theorists will say that maybe this was an implant, right? So maybe someone did it unintentionally. And because it looks so innocuous, it was a perfect thing that looks like someone was dumb and they made a mistake, but really they knew exactly what they were doing and they wanted to skip all the steps. Or maybe it was a mistake, right? Maybe it was a merge error when they were merging the code on get and they ended up with 2 copies of go to fail, or someone copy and pasted. Who knows? No one will ever know the answer to that. But because of that second line, it skipped over all of those conditions, and those conditions turned out to be really important. So they were checking important stuff. And so one of the important things that they were checking is whether the domain actually matched the domain that you were visiting. Okay, so it just skipped over it. It always returned error equals 0, which means everything passed. There was no error. And so you could, if you had a client that was using this, they were using Mac OS, and you want to impersonate twitter.com, you would just get a certificate, any valid certificate for any website on the internet, for your own website, domain.ca. And when you saw the requests go to Twitter and say, give me your certificate, you would just drop in your certificate. Even though it's not for Twitter, it's for any other website. And it would go back and the client would go through these steps and they would check it. And then before they got to that check of whether this certificate's actually for Twitter, they would hit the double go to fail, and then they would skip over all of it and they would return. Okay, so it turns out that you could basically just hand out mismatched certificates and there would be no error. Now, this code sat there, probably for, I forget how long, but probably for years, and no one had noticed it. And no one had, had noticed that there was a vulnerability in the code. Then after someone publicized it, then everyone came out of the woodwork and they said, oh, I wrote a static analysis tool. And my static analysis tool, it can just put your source code in and it will find out all unreachable code. Right, so if you would only if Apple had only run this static analysis tool, they would have caught this error, right? And so it turns out it's actually a pretty easy error to catch. because there's some code that's unreachable. Now, the problem with that story is that, first off, Apple probably did use static analysis tools. But if you use these tools, you know that the number of false positives is just enormous. If you have any kind of complicated code, you get, 5,000 false positives and 1 true positive. And so the hard part is going through the 5,000, things that it found that's wrong with your code and making sure that, those things don't actually matter, but here's the one thing that does matter. Okay, so it's not good enough for someone to just say, yeah, I have a tool that could find this kind of thing. It's like, well, how many other things did you find that wasn't an issue? That's the answer that you have to ask for. But anyways, now if they had done unit testing and they had tried to feed in certificates, like common certificates that had errors, and just see what happened, then they would have a good chance of catching this kind of error. So they need a better code review, unit tests, that kind of thing. So maybe static analysis or dynamic analysis, like these types of tools, could help. But you have to worry about false positives. After this came out, everyone went and unit tested their SSL libraries. Okay, so that was a thing, for a year or 2 years, where everyone tried every single thing that they could do. Some researchers then used machine learning and things to create, they called them frank-inserts, so they were purposely malformed certificates. They tried basically every field in the certificate. They would drop weird special characters and random things and just see what would happen. So it's called fuzzing, basically. So they fuzzed all of the different fields in a certificate, trying to see if they could get any of these weird certificates past an SSL library. So now SSL libraries should be a lot stronger than they were. And it's all it's mainly a result of this actual case study that got people to wake up to that issue. Another example of domain name matching, this one's kind of fun, has to do with null characters. So it turns out that you can, as you know, there's lots of special characters and things like that. So you have an ASCII alphabet, you have basic letters, you have numbers, and then there's some other characters that you can include. And one of the characters is a null symbol, okay? And a null symbol, it has a Unicode thing just like any other letter, but certain programming languages treat it special. Okay, so what would happen if, for example, you go to a CA and ask for a certificate So I'll denote the null symbol like this. You can do it different ways. I'll just put the dot in front of it. Okay, so what would you think would happen? So the certificate authority is just a computer. They, the code reaches this line, and it's like, hey, here's my public key. I'm domain.com null symbol.jeremyclark.com. So your computer, you're reading the string. What do you do when you hit that null terminal, that null symbol? Sorry, say it louder. Oh, you could replace it with another symbol. So no, that doesn't happen. Okay, has anyone heard of null terminated strings? Kind of, okay. Anyways, so there's a convention in some programming languages like C where, okay, the programming language you might be more familiar with is something like Java. So Java is what we call object-oriented, and if you want to create a string is an object. And so what Java will do, like in the memory behind the scenes, you don't have to worry about it as a programmer, but if you have a string, Java is going to create like a tag for the string. It's going to be like, okay, this object's a string, here's the start of the string, and then there's the content of the string, and then here's the end of the string, okay? So everything is nicely laid out. C's not like that. For C, they decided that if you want to know when a string ends, the null symbol will tell you it's the end of the string. Okay, so these are called null terminated strings. So basically, C will say, hey, there's a string that's stored in memory at this location. Go start reading that string, and when you hit the null terminal, then you know you've reached the end of the string. All right. So one thing that the CA might do is, especially if it was written in C, their code, is they might read it up to google.com, hit the null terminal, and then say, okay, that's the end of the string, and then just drop everything else. Okay. Now, another thing they might do is, well, first, they might return an error saying, okay, there's some character there, you're not allowed to use that character. And then the third thing that's common is that they just ignore it. They're like, oh, there's this character, I don't know what that is, it's not an alphanumeric character, so I'm just going to drop it, right? So I'll drop the character. So those are basically the three responses that you might have. All right, so you could terminate. So this is like what C might do. You could drop the character. Or you could reject the string and tell them to enter another string. Now the third one's probably the safest to do, but there's nothing really to say whether these are right or wrong. Now the problem though that happens is, what if different people do it different ways? Okay, so the CA, whatever, they do whatever. They look at the certificate and they decide, oh, we're always going to drop the character. Then you get the certificate and it has this weird character in it, and then you go and you show the browser. And so the browser's like going to say, okay, am I actually on the right domain? So it looks at the string and it decides to terminate the string instead. Okay, that's when you get into trouble, okay, when there's inconsistencies. So when two people look at this string and they see different things, then one of them is going to sign off on one piece of information, and the other one is going to look at it and see a different piece of information that was signed off on. Okay, so for example, if we assume that the CA does 2, so I'll just number these. So the CA does 2, and the browser does 1. Sorry, I'm getting a lot of lag still in this program. Then that's a bad combination, okay? So the CA is going to assign a domain that is what? So it's going to drop the character, okay? So the CA is going to see this as google.com.jeremyclark.com, okay? Google.com in this case is a subdomain of jeremyclark.com, so that's fine. You can call your subdomains whatever you want. And so what's it going to issue a certificate for? It's going to say, hey, you're really jeremyclark.com. Prove to me that you're jeremyclark.com. And if I can prove I'm jeremyclark.com, then it's happy to issue me a certificate for this. Okay? So the CA sees it as google.com.jeremyclark.com. And this is the top level domain, or the domain, not the subdomain. And I can prove that I own this domain, and therefore I will be able to get a certificate for this. I'm just going to explain in words because this is lagging. And then when the browser comes, it says, okay, I see that you got a certificate, and you have a certificate for google.com, null.jeremyclark.com. And let's say the browser's implemented in C, then it would say, oh, you have a valid certificate for google.com. I hit the null symbol, and then I just terminate. So I just drop the rest of the string. And so this looks like, hey, you have a certificate for google.com. It's signed by a CA. And so therefore, this is a certificate for google.com. So you could use this certificate to impersonate google.com. And you could do it without having controlled google.com. You just control jeremyclark.com. And you're exploiting that inconsistency between two implementations dealing with this special character. Yeah.
Is null character even allowed in domain name?
So now there's different rules about, they've expanded the kinds of characters, but nulls aren't allowed. It's a special character regardless. So it's never allowed. So the library needs to do something with it when it sees it. So it needs to either, say, oh, that's the end of the string. It needs to just drop it. So by dropping character, I mean like it just replaces it with nothing. Or it could reject the string and say, hey, URLs aren't allowed to have a null character. So like come back with me with a real URL that doesn't have one.
Can we say technically that it's kind of, although, can we say technically that it's the part of the CA to issue a certificate with a domain name with null character?
Yeah, so what would happen is the CA would not actually issue the certificate. Like it would strip out the null character and then it would sign everything. But then when you show it to the, so you get this certificate and that null character is gone, right? Then someone else comes to me and says, okay, show me your certificate. I put the null character back. Yeah? And then when I put it back and you do that check and you check whether the domain matches or not, then you treat it differently and then you do google.com. Yeah, so actually, maybe what I said is wrong. I actually just made that up off the top of my head. So now that I think about it, when you sign it, you're signing it at the byte level. And so that would change the signature. So then you probably get wrecked on the signature thing. So yeah, so let's say that this is a vulnerability where the CA left the string intact. So it just dropped the character when it interpreted the string, but it didn't actually change the content of what you asked to be signed. So yeah, so you actually send your certificate as a file, basically an unsigned version of it. And so it will check it all. And then when it's happy with it, it will sign that file. And so, so that's actually a better story about what happened. So apparently this vulnerability did exist in some early versions of, I forget what, it was, exposed like maybe 15, 20 years ago. Moxie Marlinspike was the person who talked about it. But there were instances where this was a vulnerability. Okay, any other questions about this? Great, let's go on a 10-minute break. So come back at 19:20. In the meantime, I'll try and get this to work. Okay, we'll start again. I rebooted my computer, so hopefully that lag issue is resolved. I was lazy, so I just copied the explanation from last year's notes. but I'll just go over it quickly. So if you ask for google.com null jeremyclark.ca, this example actually doesn't have the dot, but it works in other case. Actually, let me put the dot back in. I think it's a clearer explanation, but it does work in either cases. So let's assume that the CA just drops the null thing. Then it will say, okay, you want to register a domain jeremyclark.ca. No problem. I'll send an email to admin@jeremyclark.ca, and you'll be able to answer that. The fact that there's a google.com in front of it, it's just a subdomain. So it could be pages.jeremyclark.com, images.jeremyclark.com, google.com.jeremyclark.com. Like, it doesn't matter. It's just some subdomain. So the certificate, so this goes to the question. The certificate does, though, have to include the null symbol. Otherwise, it doesn't work. So the CA is going to sign off on the certificate with that null symbol in there. But that actually isn't as weird as it sounds, because the code that drops it is the code that's validating the file. But when it comes time to sign it, it just signs the raw file itself. So it's not changing the file that it needs to sign. Then the victim's browser would treat it, say, as a null terminated string. And so it would say, oh, this is a signed certificate for google.com. And then you could use that to impersonate google.com. Okay, questions about that? All right. Okay, so another attack you could do is you could just use an invalid certificate. So you could say, you know what, like, there's none of these vulnerabilities. This null thing has been fixed, goToFail's been fixed, all of that stuff. But still, I see the person, they're trying to go to facebook.com. I'm not facebook.com, I'm jeremyclark.com. But I'm just going to drop in jeremyclark.com certificate anyways. And yeah, their browser's not going to like it. But what will actually happen? Okay, what will happen is the browser is going to show a scary warning to the user. Right? It's going to say, oh, like, something's going wrong. Like, there's a certificate and it says this, and there's a website and it's saying this, right? And then it used to be the case that the browser would be like, okay, what do you want to do? You want to go to the website anyways? Or do you want to, like, say, oh, this is too scary, like I don't want to connect to the website? What do you think most users would do? Yeah, they see some warning about certificate mismatch SSL, and they know they just click that, like, go to the website, because they want to go to the website. They're trying to go to facebook.com, right? They click the button, and then all of a sudden they're looking at what they think is facebook.com, right? And so a lot of users would just click through the errors. Now, browsers have made it a lot harder to click through the errors. This is something that's really changed over the last 20 years. There's lots of research, especially Google's team. They have some good publications on, like, different user studies they did, trying to simplify the explanations so users would make better informed decisions. And then there's also a sort of graduated level of errors in terms of how dangerous they are. So if someone puts in a completely different certificate for another website, that's, like, really bad. Like, you should never click through that. But if the certificate just expired, like, say it was, like, supposed to be renewed yesterday and now it's today and it's a day old, it's probably okay, right? Like yesterday you would have saw that certificate and accepted it. Today you're seeing an error. Like, what changed between yesterday and today, right? Like nothing. I mean, that certificate had been around a day longer, so there's a longer chance that maybe someone had attacked it. But it's only one day. It's not a big deal, right? So an expired certificate, not so much of a big deal. Domain mismatches are a really big deal. Let's say it just wasn't signed at all, or it was completely malformed, right? In that case, like, it should not be acceptable under any circumstances. So anyways, browsers will now, for certain kinds of errors, they won't let you click through. Other kinds of errors, you have to, like, really try hard to click through. You might have to go into your certificate settings and things like that. And so anyways, I wish I could demo it, but I don't know a website that has an invalid certificate. Otherwise, I could show you what these dialogues look like. But anyways, so in the earlier days, this is what would happen is, yeah, someone would just drop an invalid certificate. So there was one example of someone that was Facebooking. It was in Syria, and they were Facebooking they were spoofing all Facebook connections. And they were just showing a CA. And in this case, the certificate was what we call a self-signed certificate. So it didn't trace back to a CA. It was just signed by the public key. Like it said, hi, I'm Facebook, here's my public key. And then the certificate was signed by the same public key that it was set. And in the early days of the internet, some people argued, well, if you put up a web server and you use a self-signed certificate, it's strictly better than not using a certificate at all. So browsers had some support for self-signed certificates, even though they weren't validated, and you could click through those warnings. And so someone just exploited that. They would just drop in this fake certificate, and they would hope that enough users click through. And there were some user studies that were done to see like what the click-through rate was if you just get average users. And 15 years ago when these user studies were done, the click-through rates were really high, like 80% or something. So people just click through the warnings. Now, like I say, there's been a lot of response to that. So browsers won't let you click through in a lot of cases. They'll make it hard to click through. They'll try and give you warnings that you can understand even if you're not a technical person. And so now click-through rates in these sort of dangerous circumstances have almost gone to zero. So there's been a lot of work on that. Okay, so let me just take a few notes about the things that we said. So the warning, so this might be like I'll say 20 years ago. You get a warning, there'd be a lot of jargon. It was written by an engineer trying to describe some technical error. It wasn't really meant for a user to understand. And you could just click through it and it usually just one click. It's just like, okay, just ignore this error. And so now we have improved warnings. Harder to click through. And so like in Safari, I've seen these warnings before, and it's like they basically give you the warning. And it's not even clear that you can click through it. But like at the very bottom, there is like a hyperlink, but it's like blended into the paragraph. And you're like, you can click on it and then you can override it. And then it bumps you over to Keychain, and it says put in your admin password because they want you to change some settings in Keychain to actually authorize the certificate. And then if you go through all of that process, then it will let you click through. But they do their best to scare you before you actually do it. Okay, the next thing is the CA flag. So I talked about this already, but I'll just take some notes on it. So a certificate from an actual CA should have a flag that says it is authorized as a CA. So we saw a picture of it. So if we compare these two certificates to each other, one of them is for Google, the site certificate, and one of them is for the CA that was used to sign Google certificate. Okay, so this one is for the actual website, Google, and you can see here under basic constraints, CA is set to no. And here for the root certificate, sorry, not the root, but the intermediary, then you can see that CA is set to yes. Okay, so there were a bunch of things that were vulnerable to this, implementations of things that were vulnerable to it. It included early versions of Windows. And the very first versions of the iPhones wouldn't do it either. And if I recall correctly, I recall hearing something else again. So it was kind of like, when it happened with Windows, everyone learned their lesson. We're like, we'll never make that mistake again. Mobile devices came out, it's different. There's a different operating system, you're rewriting it. And then they missed it. And then I think like in IoT or something, there was something recently where they had to redo their library from scratch, and then they skipped over this step. And so it's like a basic error that keeps popping up. Okay, so the last thing we'll talk about is revocation. So what if a certificate has been revoked? Okay, so what we need is a way to cancel a certificate if it's compromised. If we don't, then we could have this situation where you have a user and we have the adversary, and the adversary is holding, a compromised certificate. So I should be a little more specific about what we mean by compromise. So compromise means it's a perfectly valid certificate, okay? It was issued correctly. It was an actual certificate for, say, google.com. Okay, Google actually got it. They did it right. It's signed by the right CAs. Everything about it is fine. There's nothing invalid about the certificate. But inside the certificate, there's this key, public key, right? And the assumption of the public key is that no one knows the secret key except for the person that holds the public key. So only Google knows the secret key. But let's say the adversary was able to break into Google, or they were an insider, an ex-employee, or something like that. Somehow they were able to get that private key. Okay? So now they control, now they don't care, like say they're in the middle and someone's trying to connect to Google, they'll let Google send their real certificate because they know they can decrypt all the information that comes back. Or they can sign on Google's behalf because they know the private key, okay? So it's as good as having a certificate for Google is having the key that's inside the certificate for Google. They give you the same powers. Okay, so that's what we mean by a compromised cert. Now you can say, well, then Google will figure it out, or let's say they do. So that's a question. So maybe they never figure it out. But let's say that they figure it out somehow. One way they would find it out, by the way, this is specific to Google, is Google, they are in a unique position where they have the most popular website on the internet, and they also have a very popular browser. And so every certificate that Google's browser, Chrome, sees for google.com, the website, Chrome keeps track of. Okay, and what Google actually does is they actually hard code their certificates into Chrome. And several years ago, they decided that if they ever see a certificate that doesn't match that hard coded list, they'll immediately report it back to Google. So if anyone ever tries to impersonate Google and the victim is browsing to that website with Chrome, Chrome is smart enough to know what Google's actual certificates are, and it's going to phone home and say, hey, I just saw this fake certificate, and here's all the information about it. And coincidentally, not so coincidentally, but after they turned that feature on, there were a couple cases that were discovered of certificate authority breaches that happened. But anyways, so that's how Google would find out. So they might find it out. Now, in Google's case, they could revoke it by just updating the browser and taking it off of that hard-coded list. Okay, but so Google can do that because they own a browser. But it doesn't help if you're going to Google with Safari, right? It only helps if you're going to Chrome. And it doesn't help if you're Concordia.ca instead of Google, and Concordia doesn't have a browser that everyone's using, so we can't. And we could try to go to Google and get it to, them to hard code it, but they're not going to respond to us. Okay, so we need some sort of system to revocate certificates. If we don't, what will happen is the user will go to google.com and they'll say, okay, what's your certificate? And Google might update their certificate. So they might say, oh, I got a brand new certificate because the old one was compromised. But the adversary's in the middle, and they'll just substitute. When they see the packet go back the other way, they'll say, well, I have this old compromised certificate. And so so this means that the key was stolen. And so they'll just drop the old one in. Okay, so it's not enough to just get a new certificate. Okay, because the adversary can still show the old one that was compromised. Now, what about expiration? So eventually these certificates will expire. Okay, and it used to be the case that you would get an SSL certificate, it might last 10 years. Okay, but that's really dangerous. If you don't have a good way of revoking certificates, then if an adversary is able to steal a certificate, they have years in order to use it. And so one movement that's happened is there's been a push towards shortening the validity period of a certificate. So now it's hard to get a certificate for more than a year or 2 years. But a year is still a long time, right? If you're able to attack Amazon and intercept all the payments going to Amazon or something like that, like that's a year is a long time to be able to do that. So there are some radical proposals to shorten certificates to like they last like an hour or they last 3 days. And because we have a fully automated process for issuing new certificates, you can just get issued a new certificate every 3 days. And then you don't have to worry about revocation. If your certificate gets revoked, you just wait 3 days and then it's expired anyways. But anyways, in the old vision of HTTPS, we wanted another protocol for revoking. Okay. Now, how would you do revocation? Let's just sort of brainstorm what we would do. So idea one was that Google would just update their certificate, but that doesn't work. Okay. So somehow the user has to learn that the certificate is no longer valid. Okay, so how could it possibly learn that it's no longer valid? Okay, so it's going to have to ask someone, right? Who could it ask about whether certificates are valid or not? Okay. So I heard someone murmur Google and someone said certificate authority. So let's take them both in case. Google.com, remember, you don't know whether the certificate is even the real certificate or not. That's what you're trying to decide. So you can't ask Google.com itself whether your certificate's revoked or not. If there's an adversary in the middle, they'll just always say, no, it's not revoked. Okay? You could try the CA. So you could go to the CA. The suggestion was actually the root certificate authority. So you could trace it all back to the root certificate, or you could just ask the closest CA that issued it, because they would probably be more authoritative, whether or not the certificate is revoked. So that was the idea of revocation. So you would always check in. Technically, every single time you go and you get a certificate, your browser is then going to ping the CA of the CA of that's in the certificate that issued the certificate. They're going to ping that CA and ask whether the certificate is still valid or not. Okay. And there's two basic ways it can do this. One is it could just publish a list of revoked certificates. So this is called a certificate revocation list. Or it can put up a server and just answer in real time. So you just say, hey, I got this certificate. You don't even have to send the whole certificate. You can just send a hash of it and just say, is this, you know it's valid because you did all the signature checks and stuff like that. You just need to know whether it's revoked or not. So you could have a server. And so the protocol for this is called OCSP, Online Certificate Status Protocol. Okay, so this sounds good in theory, but let's just think exactly what's happening. Let's draw it out just so that we make sure that we understand. So I go to Google, and I'm going to skip the step where I asked for the certificate. So let's just start where they sent the certificate back. So I send back this certificate, and I want to know whether it's valid or not. Okay. So I can do I can check that it's signed and that it matches google.com and all those basic checks. I can do that first. And let's say that they all work. So that's fine. So I'm happy with the certificate. Wow. All right. So I'm happy with the certificate. My only question that remains is whether it's been revoked or not. So now what I'm supposed to do is I'm supposed to go out to the CA that issued the certificate and ask, hey, has this been revoked or not? And then the CA will say yes or no. Okay, so two questions. First question is, how do I know where to go? So I have to know. First off, I have to figure out what CA. Remember, there's 600 CAs. So which is the CA that issued the certificate for Google? Well, that's going to be in the certificate itself. So the certificate will tell me. Then, does the CA have this server online? Where is it? What address is it at? And those types of things. And so that will also be in the certificate itself. So if we go back and we look at Google's certificate, we can see that it was issued by Google Trust Services. So Google is kind of like their own CA, and that's who issued it. And then if we scroll way down somewhere, we can see Online Certificate Status Protocol, and there's a URL of where to go. Okay, so this comes from the cert itself. Now, anyone notice anything unusual about this? Anything strike you? Okay, so you'll notice that this is over HTTP. Okay, why is it not over HTTPS first? Is there a good reason why you couldn't put it over HTTPS? So the answer is that if you made this over HTTPS, then when you go to that website, you'll get a certificate for it, and you're going to have to figure out whether that certificate's been revoked. And they're going to go visit this HTTPS server over here, and then you're going to have to figure out whether that certificate was revoked, and you'll end up in this circular loop, okay? So that's why they can't put it over HTTPS, because then you're trying to figure out whether this original certificate's been revoked, and then if they send you to another server on HTTPS, then you have to figure out if that one's been revoked, and you'll just go around in a circle. Okay. Now, what's the consequence of this not going over HTTPS?
Manipulate.
Okay, so who can manipulate?
Man in the middle.
And man in the middle where in this diagram?
Between
All right, so let's say our adversary is sitting here. And so you go and you say, hey, CA, I just got the certificate from Google. Has it been revoked? And the CA is like, yeah, in fact, it was revoked, right? The adversary, this is the old certificate that the adversary is dropping on the connection. What does the adversary do? They just change the yes to a no. And then you learn that, no, it wasn't actually revoked. Okay? So that's one problem with OCSP, is that you can manipulate the responses. Another problem with OCSP is, imagine, so you saw that Google was their own CA. Okay, so that's fine. Imagine, though, that Google used the Canadian CA in trust. Okay, so there's a little CA in Canada. It's called Intrust. And Google decides, hey, we're gonna support Intrust, and so we're gonna get a certificate from them. Maybe just for our Canadian users, maybe we won't use it for everyone else. Every single time someone goes to google.com, those people are also hitting Intrust server. How many people go to google.com in a second? Yeah, millions, probably more, right? Like that's the most hammered server on the face of the earth. And so the CA has to have an equally robust server, right? So all the traffic that goes to google.ca, every single person that connects to it is now also connecting to the CA, and they're asking, is this certificate valid? Now imagine if Intrust did Google, and they did Facebook, and they did Twitter, and they did Instagram, right? All the traffic going to all of those websites, every time someone goes to one of those websites, at least the first connection, they're also hitting this server. Okay, so these servers would just get hammered as well. So it's hard. So you basically get one response. Or you have to serve up one response for every connection to your, like a website that you issued a certificate to.
Sir, is it also consume bandwidth?
Yes. So this is where it's a little different. Google, like, they get a lot of traffic, but they also have to send back a full web page, right? And then when you search it, they have to send a custom thing, and you search Google image and they send you a bunch of stuff, whatever. Whereas in this case, it's a very simple, like just, is it revoked and yes, no. Like it can be a byte, basically, that says whether it's yes, no. So in terms of bandwidth, it's small, but it's still, it's a lot of pinging as well. Yeah. Okay, so what would happen is OCSP, basically servers would never respond, at least for up until maybe 5 or 6 years ago. And so what would happen is browsers then had to decide, what am I going to do if I don't hear back from the OCSP server? So I'll try and ping them, but I've waited, it's been a second, and I have got no response at all. What am I going to do? I could either throw an error, right? I could show the user a warning and see if they could figure out what to do. I could just drop the connection, right? But this is going to affect like almost every website on the internet, or I could just ignore it, which is called failing open. And so that's what browsers did for the longest time, is they would just fail open. So you had this revocation that was in place, but it basically didn't work. So like if you stole a certificate and it was actually revoked, even if you couldn't get in the middle of that connection, there's a chance that the server would be so overwhelmed that it wouldn't respond anyways. right? And then if you could be in the middle and you did see the response, you wouldn't even have to change the yes to a no. You could just drop it. And the browsers would be like, oh, I didn't hear anything back. And then they would eventually just put the connection through. Anyways, because this was a problem for so long, browsers have now become more strict with it. So they actually started with extended validation certificates, even though it no longer shows you the difference between the two. But it said, we're going to have some new rules about extended validation certificates. So they have to be stored publicly in this log called certificate transparency. And your OCSP responders need to be live. So this is less of a problem than it was, but historically, basically, revocation didn't work. So there was protocols for it, but no one actually used it. All right, so servers wouldn't be able to respond. So these are the CA servers. And the browsers, the user's browser, they would fail open, meaning that they would see that there was a failure, but they wouldn't throw an error as a result. Now the other challenge is with revocation is think about it from the perspective of so Google, okay, we said that Google is their own certificate authority. So this is actually a nice example. Now, let's say I was able to breach some other certificate authority in the world. Let's say DigiNotar. Okay, so that was a certificate authority that got breached. So I breached DigiNotar, and I tricked them into giving me a Google certificate. So now I have this Google certificate. Okay, so I'm going around, and I'm showing it. But the problem is I accidentally show it to a Chrome user, and then Chrome freaks out, and they send a copy of my certificate back to Google. So now Google knows that, oh, DigiNotar has this, or there's this fake Google certificate, it's floating around, and it's signed by DigiNotar. Okay? Now Google, their CA is themselves, GTS, okay? And there's the fake certificate, which is issued by DigiNotar. Who has to revoke the certificate? So they want to get that certificate revoked. Can they go to themselves, to their own CA, and have it revoked? Or do they have to go to DigiNotar to get it revoked? So they have to go to DigiNotar. DigiNotar issued it, so they're the ones that are going to revoke it. They're the one that's going to have that OCSP address in the certificate. Okay? So part of the problem with revocation is if there's a bad CA out there, you have to deal with them in order to get things revoked. So you could be a company and you could have the best CA in the world, the most trustworthy CA in the world because it's you, right? Like you are your own CA, but you still have to deal with all the other CAs in the world because they have the power to issue a certificate. And if you want to get one of them revoked, you have to go and get them to revoke it, okay? So if DigiNotar was so bad that they were misissuing certificates, what if they also are like, they don't handle revocation very well? Right? Or they just are non-responsive or something like that. Yeah. Yeah, so there's no like criminal charges, I don't think that's ever been laid like for this type of activity. What will happen is, so it actually happened twice. So DigiNotar was one example, and there was another CA called Komodo. And they both happened around the same amount of time. And both of them had issued Google certificates as well as like Facebook and a bunch of other ones. So the one thing that you can do to punish them is you can kick them out of the root store. And so what happened in this case is DigiNotar was like a small CA. They were based in Norway, if my memory serves correctly. Or no, Netherlands, I think. Yeah. I think they were Dutch, and they were small, and like there was a bunch of Dutch websites that used them, but no one else really used them. Komodo, on the other hand, was this big, like huge company, and they had tons of certificates out of there. And so DigiNotar got kicked out, and Komodo was deemed too big to fail. If they kicked them out, then they would have to, everyone that used Komodo would have to go and get signed, and so they didn't kick Komodo out. And so, so it wasn't fair, right, obviously, in that case. And so that's really the only recourse that you have, is all the browsers would have to get together and they would say, we all agree to kick this person out. But then that's going to depend a lot on your business relationships and things like that. Now, if you get a root certificate, let's say you want to kick a root certificate out. So DigiNotar in this case was an intermediary. So that's easy because you can just revoke their certificate because it's in this chain of certificates. But what if you want to kick out a root certificate? How do you kick out a root certificate? So a root certificate, you'd actually have to push a software update. So there's no way to kick a root certificate out. So root certificates don't have any revocation that's applied to them other than a software update. So everyone would have to update their operating system, then you could get rid of a root certificate. So that would be even more damaging if you're able to compromise a root certificate. So if a certificate is revoked, it has to be done by the CA that issued it. Okay, and then I'll just note that there's a couple of fixes to revocation. So the one we mentioned already is that now we require, and by require, the threat is that you get kicked out. So if you're seen not being able to handle our OCSP responses, then you basically get kicked out by all of the. So all the browsers came together and they formed a working group called the CAB form, CA/B certificate authority/browser. So it's all the certificate authorities and all the browsers. And so now they start to coordinate a bit in terms of responses. So we require OCSP liveness for EV certificates. And this may have been expanded in the last year to non-EV. I'd have to check. And the other thing is that Chrome started going around. I said there's also these certificate revocation lists. And so Chrome made a point of going around and collecting CRLs for you. So instead of you seeing a certificate for the first time, then you going to the CA and trying to figure out whether it's revoked, it just, Google themselves as a company, they just, once an hour, they go to every CA they know about and they say, give me your latest CRL list. And then they have it as a file. And then your browser, Chrome, once an hour or whatever, will go to Google and say, give me the latest list. And then you check everything client side. So Chrome pulls all CRL, certificate revocation lists, into it for the user. And I don't think it would be once an hour because usually these, actually I don't know what update frequency, but CRLs themselves usually take a couple days to be updated. And all of revocation works on kind of like a 3-day window. Like by the time you get it revoked and you get the server updated and then the server is like talking about it being revoked and things like that, you usually can't get anything done in less time than like about 3 days. And so the advocates of short-lived signatures say, or short-lived certificates say, let's just issue certificates that are 3 days. They expire after 3 days because it takes that long to revocate a certificate anyway. Then we don't have to revoke anything. We just let it expire every 3 days. But anyways. Okay. So the last thing I'll draw your attention to is the reason we were doing all of this is we're trying to come up with this big attack tree for all the things that can go wrong with HTTPS. I'll show you the attack tree from last year because I haven't updated it this year, but it's the same essentially. So it's already on the course website. So if you go to any of these lectures and you click on tree, it always gives you the same link. And so, so what I did is I tried to put all of the things that we've talked about in the last couple classes into a single tree. Because it's from last year, the numbering's a little different. We called this number 2 and we called this number 1, but just there's some minor things like that. This also I would put in a different spot. So at some point I'll go in and fix this. Unfortunately, I lost the source code to generate this tree. Otherwise, it'd be easy to update. But anyways, so first we said, well, maybe you can get the cryptographic key that protects the tunnel, and then you could attack the protocol, attack the crypto. You could try and downgrade those kinds of things. Then we said you can learn a lot just by looking at HTTPS, even if you can't decrypt anything. So you fingerprint the traffic based on the size of the images coming down and where they're coming down from and things like that. You always know what domain's being visited, even if you can't read the content that's being exchanged. And then we said, okay, let's try to subvert server authentication. So first off, we can try and get a valid certificate. So to do that, we could hack a certificate authority. So DigiNotar and Komodo are two examples where someone hacked them and were able to get certificates for it. We could somehow subvert the issuance process. So if it's an automated process for domain validated certificates, I gave the example of email, but it's pretty similar for anything else. So you could guess the email password, you could guess the DNS record password, you could lift the secret out of the email as it goes across the wire because it's not encrypted. You could try and change the mail server to point at your mail server. You could try and get one of these email addresses that's supposed to be reserved but isn't actually reserved. And then if it's an EV certificate, that's an in-person process. So we gave the example of social engineering. So someone that was an ex-employee of Microsoft was able to get a code signing certificate because they still had enough credentials to do it. You could, if you're a government, you could go and say, hey, you're a CA, you're in my country. I command you by law to give me your keys. And then you could issue certificates. This we didn't talk about, so I'll just skip over it. You could just use an invalid certificate. So you could either just tolerate the error or the warning and hope that the user clicks through it, or you could exploit some problem with the implementation. So maybe they're not checking whether it's a CA or not. Maybe there's like go-to fail, so there's a mismatched domain that's not being checked. Maybe there's some parsing error because there's a null character, that kind of thing. Maybe you're able to obtain a certificate, but then it gets revoked. So now you shouldn't be able to use it. But because they're using OCSP, you can just, if you're a man in the middle on that connection, then you can just drop the response when the user asks the CA whether it's been revoked or not. The last thing you can do is use no certificate at all. So yeah, I forgot. This is one thing I want to talk about. So you can do what's called Ssl stripping, or you can do a picture-in-picture attack. So let me just explain these quickly. Okay, so generally what would happen is, this also is somewhat outdated, but I used to give the example of the New York Times many times in the past years, but unfortunately fortunately for security's sake, but unfortunate for this course, they fixed it. But normally what would happen is you would go to a website like, say, the New York Times, and you would get the front page. So let me put news.com. This probably is a real site, but I don't mean the real site. I just mean an arbitrary news website. Okay, and there's no like real compelling reason to log into the New York Times, right? Like now maybe like you have to log in to see the article or something like that. But like there's a lot of websites where they have some user account that lets you do something, but it's not like there's some sites like Twitter that like if you're not logged in, it's useless, right? And then there's other websites where like they have the ability, like Concordia. Concordia is a great example. So you go to Concordia, you can log in. There's certain websites within Concordia that let you log in, but there's tons, probably 80% of Concordia you don't have to log in to see, right? All right, so websites like this, usually what they would do is they would start on HTTP. So they would give you, for example, what's called a landing page. So that'd be like the first page that you land on. And this would come over just HTTP. Okay, and if you looked closely at the website, you would see a website that looked probably something like this. So you had a bunch of content on the website, blah, blah, blah. And then on maybe in the toolbar, like in the upper right-hand corner, there would be a little like field where you could log in. Sorry, that drawing program's going crazy again. Okay, I'm just going to explain it with words. Okay, so you would have a little thing in the upper right-hand corner. It would say, "What's your username? What's your password?" And then there would be a submit button. Okay. Now, if you click that submit button, you're about to send your password over the wire. Okay. And you want to send a password over the wire in HTTP. Do you want to do that as a user? No, you don't want to. You want it to go over HTTPS. Okay. So that's great. What they would do is for that button, the submit happens by posting information. So posting is just, you can get a HTTP page or you can post whatever. But the URL for the post would be over HTTPS. Okay? So you would download the website, the front page, and even though you got it over HTTP, if you actually put your username and password and hit that post button or that submit button, it would send it over HTTPS. Okay, and then when you come back and it says you logged in successfully, you would actually get that page back over HTTPS. And then they might bounce you back down to HTTP, or they might keep you, now that you're logged in, they might keep you on HTTPS forever. So that's up to the website to decide how to do. Okay, now is that secure? If you want to give the user an HTTP site initially, and then you make really careful, you're a really careful web designer, you make sure that all your, every time you submit a password or something like that, you're going to submit it over HTTPS. Is that good enough? So people are shaking their heads because obviously I wouldn't ask the question if it was good enough. But can anyone think of what the flaw is?
It's not good enough.
It's not good enough. You're correct. So what's the flaw now?
Okay, so let's say there's a log, and the log end there is like safe password. This mechanism. So what we do is usually we save the cookie. So the next time I log in, I access the website. It's over HTTP. I can see all the cookies as an attacker. So I can get the cookie and then use it. So I am technically.
Okay. So there could be something with once you've logged in, then they're going to create a session password for like a session cookie secret value, and anyone who can steal that value can hijack your session and be logged in for you. So that's true. Let's set that attack aside. Is there anything else? Something simpler?
Someone can take the page, and because the submit button is actually behind the scene, so they can actually replace the submit button URL with something else. Provide the page to the user. So every time they click the submit button, it actually goes to them. But afterwards, what they do is that they forward the request to the original HTTPS website themselves. So the user sees that they have logged in. So from a user perspective, everything is fine. But in the meantime, through a man-in-the-middle attack, they were actually able to capture them.
Okay, so that's good. That's 1 degree more complicated than it needs to be, but that's exactly right. So when the HTTP site comes down, if the adversary is in the middle and they're an active adversary, so that means they're not just listening. They can listen. They know everything because it's over HTTP, but they can also change it. What they can do is they can actually change the content of the website. So the fact that you're submitting over HTTPS, that instruction to submit over HTTPS is in the content of the website itself. That's content that you downloaded over HTTP. So what they can do is they can replace that URL that you submit to with anything in the world that they want to. Okay? So you could have your own custom server set up and then it submits to you, and then yeah, you could relay it to the real website and then go back and forth. An easier thing that you could do is you could just write a script if you're the person in the middle, and every time you see HTTPS in the content of a website, you just drop the S. Okay? So now what happens is the submit button comes down, but when you click on it, it's actually going to go over HTTP. It's going to go to the real server, so it's going back to the New York Times. So everything is good, but it's going to go in plain text instead of encryption. Then you can read the password out. Now, how does the user know? Let's say you're sitting on the New York Times website. You see that it's HTTP, that it came down over HTTP. You see that submit button there. How do you know whether when you click on that, it's going over SSL or not?
On the bottom, left bottom of the screen, you will see the URL, and you will know if it's HTTP or HTTPS.
Okay, so it's possible that if you hover your mouse over the button, it might show you the URL. Generally, it's not going to do that with posts. So it might do that with a link to follow. But this isn't a link. It's a post request.
You have to use the developer tools. You have to use Inspect.
Okay, exactly. So basically, you can't see it. There's no way. What if there's a lock? Like, say the submit button, and then there's a little lock beside it. Why not? You'll see that a lot, right? There'll be a username, a password, then there's a submit button, there's a little lock in the submit. So that means it's over SSL, right?
Yeah, there's so you can change the bottom.
Okay. So the lock is just a picture, right? So the website can put any picture there that they want. They can put a lock. It's in the content of the website itself. So yeah, a little picture of a lock. And some websites put locks everywhere. It doesn't mean anything. So there is no way to know. If you were to use the developer tools and look at the source code of the website that you received, then you could find that button and maybe see whether the URL goes over HTTPS or not. But generally, you won't know. Now, one way you'll know is after you submit whether it comes back to you over HTTPS. But then it's too late, right? So you can plug your nose, hit submit, cross your fingers. But then if it doesn't come back over HTTPS, you just sent your password. And it's too late at that point, right? So you get that feedback, but it's too late to do anything about it. So anyway, that's called SSL stripping. It's very easy. You just strip every reference you see to HTTPS, and you replace it with just normal HTTP. There's one other attack called picture-in-picture, but I'll save it for next class because we're out of time. So thank you, and I'll see you next class.